All right, folks. So I'm going to just do some sound checking here, making sure everybody is able to hear me properly, and then we will get started in a moment or two. So this is the live stream about Android security internals, and I hope everybody is able to actually join in, and otherwise I hope you can catch up with us a bit later with the recording. So my name is Kareem Yakmor, and in the next hour or so we are going to look at how Android's security works, and if you are having any issues along the way, please let me know over the chat, and I will try to help you out as much as possible. There is a private channel, and those of you who are joining over the private channel will have to refer back to the conference bridge information to be able to get voice. Feel free to join in whenever you can do that. So whether I get answers in the private channel or off of YouTube Live, then I will repeat those for the benefit of the larger crowd. So I am using a different, a whole bunch of technologies here to monitor what is going on. So if you see my eyes going over or me picking up the phone, that's just because I'm checking if things are moving properly. Okay, good. This is good. Alrighty. Now, Android security is pretty complex these days. There is a lot of things happening under the hood. I'm going to try to give you a survey of what's going on, but there are things which I will not be able to cover given the short amount of time that we have at our disposal. What I have done, though, is I've put online on our website a set of class material that we had been developing for a while now, and that we just published yesterday. And it is actually a full-fledged, complete class with 300 and some slides about Android security internals. So you're free to go look at those materials for more in-depth information. Alrighty. So yeah, this will work better if I actually do connect it. Give me 1 second. Okay. All right, just one thing about the slides for everybody's benefit. So I will put those up once the session is over. There is, quite a few things that I've gotten from third-party sources. That's just because, as I said, it's pretty complex, so it's hard to kind of create everything from scratch. If you do see material that is in there that is yours and you don't like our use of it, just let me know. We'll just take it out, all right? Otherwise, the slides are going to be online after the presentation. So for those of you who don't know me, I wrote the Embedded Android book for O'Reilly. I wrote the Embedded Linux book for O'Reilly. And I've been involved in open source for 20 plus years now. And I'm most widely known for my contributions to the tracing work that has been done in the kernel. Fortunately, there's a lot of very good people doing much better work than I was back then, and I'm happy to have other people take care of it than myself. All right, so what are we going to talk about today? So we're going to look at the chain of trust. How does that actually work? We'll look at some SOC internals. So there's, Android is a software stack, but there's a lot of things that happen with regards to security that are, very much hidden into hardware. And so if you look at the information that is provided to you by Google, it tends to be fairly generic. And therefore, there are things that you have to refer back to the hardware to understand what's going on. And so hence, we need to take a bit of a step back and look at how system-on-chip chips actually work. We're going to look at the general system architecture, and then look at secure booting, TrustZone, the high-level operating system, what it gives us, SELinux and SEAndroid, some stuff about the user space, and the cloud, how does that all kind of come together? But the root of it really is hardware. So if your hardware is not secure, you've got nowhere to go to start with. Okay, the chain of trust. So obviously, the very first step here is to have silicon that is trustable, PCB, and then the software that comes on top of it. So this is a diagram that I've been dragging over, from into a lot of presentations, and it just gives us a good idea of what parts are making up the system. We got an application processor on which Android runs, the baseband processor, which talks to the cell tower, and then effectively what we're trying to understand here is how this system on chip is being secured. Okay, here's an interesting quote that I like very much. So it comes from Ken Thompson, who's one of the creators of Unix, and he was doing a lecture for a Turing Award, and his paper that he did for that talk was effectively a compiler hack, which shows how you can make a compiler that generates code that actually contains, so to speak, malicious intentions and whatever, and then effectively it becomes replicating. So insofar as you have that baked into the compiler, it effectively becomes invisible, and there's actually no way to detect it. And he kind of says this, in this demonstration of the possibility of this kind of attack. I picked the C compiler. I could have picked any program handling programs such as assembler, loader, or even hardware microcode. As the level of program gets lower, these bugs will be harder and harder to detect. A well-installed microcode bug will be almost impossible to detect. Which actually we see these days with all these issues that some processors are facing with Spectre meltdown and the more recent ones that were exposed this week. So if it is a hardware issue, there's practically nothing in the software that will allow you to actually see what is going on. So that's a problem, right? So we have to understand how Android is secured at the hardware side in order to be able to get to see how the software itself is secured. And if you don't believe me, I put a few links here for some hardware that I found that you may have fun actually playing with. So you've got things like the JTagulator. So the JTagulator is an interesting piece of hardware that allows you to effectively connect a bunch of pins to it, and it will go around and tell you which one of these are actually JTag pins. So that's pretty fascinating. So in other words, if you design a board and you try to hide the JTag functionality by just not marking it on the PCB and just having these exposed headers somewhere, well, somebody somewhere could actually find those. So you either want to disable those completely in the hardware eFuses in the SOC, or just don't route those on a PCB. Bus pirate is an interesting thing. So effectively, you can connect a whole bunch of signals to this and actually watch them. So insofar as if you've got nice I2C or anything else of that kind exposed, then certainly you can read what's going on there. If you want to take this a whole other step further, you've got DDR analysis tools. So anything that comes out of the SoC and goes off to the data bus could be snooped on. So you can't trust that insofar as it actually goes out of the processor. You have to assume that it could be readable. So in other words, you can't put secrets in plain RAM. It has to be secured in some other fashion, either on the chip itself, never leaving the chip, or encrypted in RAM, whatever it is that works, but don't actually leave anything in RAM that you think is truly valuable. And then you have a whole bunch of other things like logic analyzers, JTAG tools. You can take this further. There's even some stuff that you can buy on AliExpress or other places that allows you to just effectively just remove flashed content from eMMCs and other sorts of things. So if you store stuff plain text into a storage device, even if the software has its own controls, you have to assume that somebody could unsolder that chip and go and get it. So there has to be more than just storing to the chip, to the eMMC. Now, there are also USB analysis tools. There's protocol analyzers in software like Wireshark. There's this IDA tool, which is very often used by reverse engineering folks to reverse engineer assembly. It's pretty effective. I mean, a lot of the exploits out there that document their exploits will be using stuff like IDA. There's this very interesting cold boot attack called Frost. You can go check out their website. So effectively what they do is they boot a device and they put it in the freezer and very quickly swap batteries, and then upon, they take the battery out and put it back in, not swap batteries, but just really quickly put it back and out, and then they boot a custom image of theirs through the recovery mode, and then given that the RAM hasn't had the time to erase itself, they're able to recover from their alternate image pictures and data from RAM. So this doesn't even require any sort of hardware here. It just requires freezer and good hand-eye coordination or timing or sleight of hand to get it to work. And if you want to see what people can do in their free time, there's a whole bunch of hacks on Hackaday, the website. And so one of these, this reverse engineering, the PSP is kind of entertaining because you can actually see somebody that, if I can get my mouse to work here, I apologize, my laptop configuration is a bit weird where I can't actually watch my own screen to see what's happening. So I'm going to try to do this magic by hand. Let's see if I can make this happen. No, that's not what I wanted. Right click and then open link in new tab. There we go. So you can see here on this picture, the gentleman effectively kind of got all these wires hooked onto this PSP and kind of reverse engineering the whole thing. So if people have free time, they will do interesting things, and a lot of people have free time. So if your hardware has any sort of vector of attack that can be kind of hijacked to give access to stuff, people will find it. So you have to really understand what's happening from a very early on in the boot process to know how to actually take care of problems. All right? Okay, so on the software side, obviously, once the software comes into play, then you have a whole bunch of things that happen, and every one of those links has to actually secure the next step. First, the hardware has to check the software, and then every chain of the software boot process all the way into the cloud has to actually check the next step. If any of these things doesn't do its job or has an issue, what will happen is effectively you will be able to hack the system. All right? Okay. So what does Android's architecture look like? I have other videos on YouTube that you can consult if you want me you want to hear me do a detailed walkthrough of this. But effectively, this is the same architecture diagram that I've been using for a very long time. Linux kernel at the bottom, giving us effectively the base of our security and user space. You've got some native user space components on top of which you've got a Java layer. The most important thing up here being the system services, and then on top of that you have the actual applications which are running on top of all that. So every piece of this puzzle here has got some security related to it, of various complexities. Some things are more complicated than others. All right. Okay. So let's take a look at how system-on-chip systems work. What does it look like? And in as much detail as we can actually get here to get a good idea of what it is that we're trying to secure and how does the hardware enable us to actually secure those things. So this is a generic diagram of a system-on-chip. Whenever you talk to any specific vendor, they will have their own kind of diagram to show you in their documentation. In the case of most SOCs that are used in Android devices, it's going to kind of look like that. So you got a bunch of CPU cores, a GPU, and then a whole bunch of peripherals, all connected through some form of interconnect, which we'll take a look at in a few slides. So if you look at, for example, an ARM-based processor, and so this is a diagram that I got from an ARM presentation. So the interconnect here has the processor cores which are attached to it, got a GPU, and then they've color-coded kind of a few components there with regards to security and trust. And we'll see some variants of this diagram a bit further down the road. So in this specific diagram, the blue stuff is trusted. The kind of semi-blue stuff is switchable between trusted and normal world. And then the blank stuff is just non-secure, all right? So you can see here you've got trusted SRAM, and again, this is effectively, on-chip memory. So this is effectively on the system on chip. There's going to be on the die a bunch of RAM. It's not very big, but it's big enough to actually load some early boot code and say the trusted execution environments, which are now running inside the chip, not outside the actual buses coming out of the chip itself. So it is kind of trustable to a certain degree. Now, if you want to take this a step further, there are techniques to actually uncap processors and use electron microscopes or whatever else to actually take a deeper look into what's happening on those chips. The question is always, how expensive and how complicated the attack is. We humans are pretty clever, so there is a possibility that somebody has enough money and enough time and enough desire to actually crack what it is that you've got in your hands. But for, say, a general purpose system, then having stuff in the on-chip RAM is a fairly secure way of handling the information that's going on there. Okay, so moving on here a bit further down, so another diagram again from ARM. Again, so the color coding, so the actual dark colored stuff is secure. The kind of a pinkish thing here is semi-secure or configurable, and then the clear stuff is not. The interesting thing is in a processor like this, you can configure the different units to say, okay, this unit can only talk to the secure units, or kind of have some rules that say these different units can interact in these different ways. And the TrustZone stuff that ARM has ties directly into this concept, because as we'll see, effectively the CPU has two modes, or the cores have two modes of operation, and when they're in TrustZone mode, then there's different things that happen on the system. Specifically here, what you see, again from another ARM diagram, is the secure bit, and so it's either secure or non-secure. And so when the chip itself, the ARM core, is running in TrustZone mode, then the secure bit will be set in on the bus, on the actual fabric, and therefore it will allow the core to communicate with some secured units or subsystems. And if it is set as non-secure because it's running, say, Linux, then in that case it can't access those units or those memory regions or what have you. Okay, and here's another diagram that shows you how this actually maps down to memory. So you can actually chunk up the RAM to say these regions are secure, these regions are non-secure, and depending on whether you're in TrustZone mode or not, then you will be able to access those regions or not. Okay, so this is something that is also a key to the security functionality on processors. Alrighty, so this is effectively the software kind of architecture that is layered on top of what we just saw, which is the hardware that enables us to actually have secure and non-secure capabilities. So on an ARM 32 processor, you can, and I'll start with that because it's kind of like the simpler diagram. You will see here that we've got the non-secure world, which is effectively, say, Linux, with applications running on top of it and possibly a hypervisor. When the processor switches over to secure mode, all right, the main operating system, the higher level operating system like Linux, doesn't see what's going on the other side of this wall. And effectively here we've got a trusted OS and some applications running on top of it. They're called trusted applications, or TAs. And those TAs will be running on top of a operating system that gives them effectively capabilities, much like Linux gives capabilities to its applications. This will have its own capabilities. And so the switching between these two modes is done by a specific call an assembly on the ARM side, and it's called SMC, so Secure Monitor Call, and that allows effectively Linux to switch over to this secure mode, and then effectively Linux kind of doesn't see what's going on, but really switching operating systems into a completely different state of the processor. Yeah, and so one thing I wanted to point out is applications can't actually use this call, right? This is something that the Linux kernel can only do. And so the applications would generally talk to a driver on the Linux side, and the driver would actually make this call on their behalf to switch over to the secure mode of the core. You go into 64-bit ARM, the left-hand side of the diagram, the non-secure side, is practically the same. However, now the secure side has kind of become a bit more complicated, and what you've got here at the bottom effectively is this thing called ARM trusted firmware. And this is something that ARM puts out and is open source, and then allows the processor to run a number of trusted OSs, sometimes one, sometimes a few, depending on the system that you've got, and the rest of the architecture here is a bit the same. And the switching is also done the same with this SMC call and so on. And when you do an SMC call, be it the secure firmware, ARM trusted firmware, or the trusted OS in 32-bit, is going to switch some registers, save state, and then effectively put a new state in so that the secure applications can start running. Now, if you look at the a bit more detailed view of this diagram, you can see here effectively the trusted world versus the normal world. So when you've got Linux here making calls, they're calling into the trusted firmware or to the secure monitor, and then this sends it off to the applications, which will then talk to the applications. And in terms of booting, in terms of booting, it kind of goes this way around. So you've got the first stage bootloader, starting second stage bootloader, and then which started trusted OS and firmware, and then the normal world. Sorry if I can pronounce that right. Will eventually kick in. Okay. So what can you do to actually attack a system on chip, an SOC? And this is stuff that's out there. I kind of just made a bullet list, but you can Google any of these things and find either research papers or exploits that have been made using those techniques. So probing exposed pins. I mean, that's a classic. If it comes out of a pin, then somebody somewhere can probe it. That's just it's just too easy. If you've got JTAG exposed, that will be findable. I showed you, I mentioned a tool earlier that can do this, and anybody can find those pins, can then attach a JTAG, a debugger, and then have fun with that. There are also side channel attacks, and there is quite a few of those. So cache attacks, cache timing attacks, effectively just play with an application doing some specific access, and then all of a sudden the cache is going to spit out at you information or leak information that you're not supposed to have access to. Power monitoring attacks, where effectively you put some load on the processor and then you check how much power is being used, and using that you actually kind of gather information about what's going on. Electromagnetic attacks, differential fault analysis, a whole bunch of things that that can be done, including acoustic attacks and so on. And at the end of the day, as I said, you can always decap the chip, and if you have the proper equipment, look at what's going on inside of it. And again, this is it just gets more expensive as you're getting closer and closer inside the chip. There are even chips that have countermeasures that if you uncap it, it's supposed to know that it's been uncapped, and then effectively allow you to kind of have some sort of a countermeasure in those cases. Okay, so assuming that our chip is secure, and that we can trust it, and that we've engineered our system in such a fashion that the hardware is trustable, how do we get into running some secure software, or software that we know about, or the chip from factory is going to be able to check that this incoming software is effectively properly signed by us, or that it was minted by us and not been hijacked or tampered with, or whatever else. So this is this is kind of my attempt to show you how the system boots in a secure fashion. And this is just a simple view. I'm only addressing here the early boot process. I haven't gotten into Linux and then Android. I'm just really just talking here about, okay, how do I get a system that is effectively booting known software? So Okay, I've kind of tried to color code things here, but I'll kind of walk you through here in as slow a fashion as possible. So we've got in this system on chip. So this is what we've been talking about here for a few minutes. In the system on chip, I have a few important things. First, I have some eFuses, and I'll mention to you what eFuses are in a bit more detail later on. Or I think I skipped. Did I skip the slide? I'm sorry. I'm just going to go back here. I think I skipped the slide somewhere, or I did not. Okay, I think it might be a bit later then. Sorry. Okay, so okay, eFuses are effectively it's like a fuse, right? As you might think of a fuse, you put too much current and it blows. Except these are one-way fuses on the chip itself, and they're going to be used at factory time to burn some information on the chip. And once that's burned, you can't actually kind of change this. And so what's going to be used, what's going to be put in some of the eFuses is a hash of a root certificate. So it's not going to be the root cert itself, it's just going to be a hash of it. So we're going to put in the eFuses the hash of our key, in the case of us being a manufacturer of a device. We're going to have some crypto hardware. We're going to have also on the chip a primary bootloader. So there is code that runs off of ROM that is in the SOC. When you put the power onto the SOC, it's effectively going to start booting that. And the job of this primary bootloader is to go and load additional bootloaders downstream from it, right? And one thing it is going to use to check that those incoming bootloaders have the right to boot is whether the signature has been properly set or they've been properly signed. And then you've got TZ here, which is my TrustZone capabilities, which is what I had mentioned earlier, allowing us to run some trusted OS with trusted applications on top of them. Okay, so I put here, and I kind of tried to do some symbols here where effectively this dot thing means it's signed with or includes. So the OEM root CA cert hash is burned into the eFuses, and this kind of takes me to this side map here. So the OEM root CA cert signs an OEM attestation CA cert, which signs an OEM attestation cert, and that is going to be used to sign some of these components here. So for example, the secondary bootloader is going to be signed with some of these OEM certs, and it's also going to include this chain of certificates inside of it. The primary bootloader is going to check the incoming bootloader's signature by checking that the hash of the root cert matches the hash that it has in its eFuses. So in other words, from factory, we are burning the eFuses with a hash, and the incoming image is going to include certs, and those certs have to match that hash. That's how the primary bootloader that's on my SoC knows that what's incoming here is legit, all right? And so effectively it boots the secondary bootloader, and then the secondary bootloader so in the case of some Android systems going to boot this thing called little kernel, but since Android or Google doesn't specify which bootloader you can use, you could use anything that you want. But let's say we're using little kernel. Little kernel, there's an upstream little kernel on GitHub. That's usually not what the SOC vendors are using. Instead, they're using their own little kernel variation of that. And then effectively the OEM gets their tree from the SOC vendor. The OEM signs their little kernel with their OEM key, and then that essentially gets sent on the device to be booted by the secondary bootloader. Same thing with the trusted execution environment. I put this upstream TEE, trusted execution environment, which effectively is the environment running on TrustZone in dashed lines, because we'll see later it gets a bit more complicated with that. There's no single upstream TEE. So that is used by the SOC vendor, or the SOC vendor may even have theirs. At least one SOC vendor has theirs. And then the OEM is going to get the trusted execution from the SOC vendor. They're going to sign it with their own private key. And again, this is something that the secondary bootloader is going to be able to check. So from the moment I put the power onto my chip, it is able to make sure that whatever's coming downstream here is properly signed by the same person or same entity that effectively put this device out on a factory and program it at factory, because the eFuses here are going to link the entire certificate chain to this hardware. All right, so this is how we get trusted boot. And so this is the earlier diagram here from ARM, but with effectively the boot process. So when you press on reset, you go into primary bootloader or BL1, goes to BL2, which then boots BL3 and BL3.1 and 3.2, and then gets us into user space. And every one of these steps effectively is checking the signature of the subsequent step. And I'll show you another diagram here that shows us how this takes us all the way up into Android. So one thing that, at least personally, I was trying to understand when I was trying to figure out how this security, all the security is held together in an Android system is, okay, well, if I'm trying to secure stuff, I have to know where it runs, because effectively if I'm out of the chip, then I can no longer trust what's going on. And so it's interesting to see, where the bootloaders actually run. So effectively, and as far as I can, gather, because all of these things are, oftentimes, behind NDAs and so on. And so whether I know this information from elsewhere, I can't disclose. But effectively, from the public sources that you can find on the net, this is what you will find. Effectively, you've got the primary bootloader, and effectively the resource power manager or whatever else. Bootloader will have their own ROMs and RAM, and they'll run from there. Secondary bootloaders 1, 2, and TrustZone will run from on-chip memory. This is OCM, and then that will then queue in an actual high-level bootloader off into RAM, which will then effectively run the HLOS, the high-level operating system, Linux presumably, onto RAM. Okay. So speaking of bootloaders and little kernel, so as alluding to little kernel earlier, so Google doesn't actually mandate a bootloader. You can use whatever bootloader you wish to use. A lot of Android systems actually use U-boot. Others use some other bootloaders as well. So the vendor decides what they give you. You just go with what they have. It's not really something that you're going to want to mess with unless you have some very specific needs. So the little kernel project is on GitHub. It's effectively kind of like a very tiny executive. It doesn't really do much, and it's not really bootloader specific. But the bootloaders based on it use this as their source. However, they're going to add a lot more stuff to it. So there's a tree on Lenaro's Qualcomm landing team that has effectively the stuff in there. And if you want to see, for example, the internals of the LK for the 410E board, you can check on this document here. All these blue things are actually links. So when I put the slides up, you'll be able to just go ahead and click on those stuff and actually go and explore these different links if you want. Okay, so which brings me to this concept of locked versus unlocked bootloader. What is all this business about? So this idea of locked versus unlocked bootloaders is very much an artificial distinction that is made in the bootloader. And this is a decision that is made by the OEM, whether to enable the bootloader to have an unlocked mode. And what that will do is effectively allow you to boot something that may not be properly signed or be signed with an alternate key or what have you. So it's very much a policy thing. It's not something that is tied into hardware or anything else. It's really just a policy of the OEM as to whether they want to enable unsigned content or images to be booted or not. So interestingly, the lock state can be communicated back to the trusted execution environment at boot time. So in other words, if going back to my diagram from here, so if the secondary bootloader is the little kernel here is about to boot into something that is non-secure, it could then tell the trusted execution environment, hey, by the way, I'm going to boot something here that wasn't officially signed by us. And then the trusted execution environment can then decide to do things differently. And obviously this is at that stage, once that's being set, there's nothing that Linux could do later on or Android could do later on to kind of circumvent that. It's because the T is invisible to Linux. All right, so for example, attestation, which allows effectively, it's a functionality in Android that allows a cloud service to check whether the device is running a properly signed image. is going to use this functionality. It's going to rely on this to actually check that the TE knows that whatever booted was really legit, and if not, then whatever it decides to do whatever it wants to do. Okay, so the build system of a little kernel is a bit like Android in terms of how it works. If you're familiar with the build core and the build env setup sh and all this kind of stuff, we're in this. You'd be in familiar territory looking at the sources of that. The apps of little kernel, it has got these sort of apps are listed effectively in a table, and they're started as threads. And if you go look at the tree from Linaro here, you'll see actually some that have fast boot functionality and so on and so forth. And as I said, effectively little kernel is just a basic, executive with some operating system primitives like other operating systems. Okay, which gets me to TrustZone and trusted execution environments. So what are we, what are we facing when we look at that? So the trouble is, a lot of the actual detailed information about TrustZone is not available publicly. It's all, effectively under, tight curtains and so on. So one thing that I found pretty useful about for finding out information about TrustZone is effectively to just look at exploits that have been made on TrustZone and trusted execution environments. The guys that are doing that are, in my book, they're geniuses. But they're able to gather a lot of information about what the trusted execution environments do, what are the constructs that use, and so on and so forth. So if you're trying to find information about those things, generally exploits are a good place to start. And I do have some pointers. I can't remember if I have them in this slide set. Otherwise, they're in the class slide set that you can get. Sometimes what you'll see is that general purpose processors that you get off the market don't have the TrustZone capability enabled. So that's another complexity here, is how do you play with TrustZone? The folks at Linaro have some good instructions on how to play with TrustZone with opte on the high keyboards. So that could be a good place to start. But otherwise, there isn't, say, compared to, say, Android or Linux, a lot of information available to us. Okay, so as I said, the TrustZone capability and the trusted execution environments have hardware backing. Without that, they are of no use, right? So the processors boot in secure mode, and the peripherals are going to be either secure or non-secure, depending on the kind of configuration that you're going to give them. And as I showed you earlier, there's a secure flag that is carried over on the internal buses of the SOC, and then it will tell the peripheral, are you secure or not, or is this coming from a secure party or not? And obviously cache knows about this, and so on and so forth. All right. So usually what will happen is the internal memory is going to allow us to run the secure stuff. And by the way, they are reset on reboot. There's a couple of papers that I had read where people were trying to find out if they could do some cold attacks on the chips, and they found that they couldn't ever read anything, and that's really because at boot time the SRAM is erased. Okay, and so here's yet another diagram from ARM showing us the secure versus non-secure world versus the configurable world. So trusted RAM, trusted boot ROM. So here we have effectively the initial bring up of the processor that allows us to get into a secure mode of operation. And then effectively you can see all this green stuff or greenish stuff. I don't know how that'll show up on your side, or cyan colored, or so effectively this is configurable. All these things are configurable as being secure or non-secure. And the processor cores themselves obviously are going to switch between secure and non-secure, but when they do this secure monitor call, and they're running TrustZone and the trusted execution environment and whatever else. Okay, so this is the call that I've been mentioning earlier, secure monitor call, which allows me to switch from my regular high-level operating system into the trusted execution environment. And then effectively ATF, which is untrusted firmware, is going to allow me to switch between the non-secure versus secure mode. It does all the register switching, which I mentioned. Here's a specific diagram that shows this in a bit more detail. I took this from Linaro Connect, I can't remember what, in 2014. So you're doing an SMC call, gives us into trusted firmware, and then off to the trusted OS to dispatch your calls. All right. What do trusted execution environments give us? They are an operating system. All right. So scheduling, IPC, whatever else. It is not a very open world. I mean, I'll show you later, there's at least 2 open source implementations, but the most widely used implementations are proprietary, and so your mileage will vary with regards to what information you can find about those things. You'll have to talk to the different vendors and see what they can give you. Okay, speaking of which, so you've got the Qualcomm Secure Execution Environment, QSEE. There's a Trustonic, Kinibi. Those seem to be fairly widely used. There's obviously no numbers available that I could find. If you know those numbers and whatever, that'd be great. Trusty is maintained by Google. It's an open source implementation, and it is also based on Little Kernel. Little Kernel actually serves a few different purposes at Google, including, I believe, it is partly used in the Fuchsia stuff they're working on. Correct me if I'm wrong, let me know, but I think that is the case. And then you've got opte, which is open source, and it turns out that opte seems to be the one that I can find most information about, and that there is code that you can actually play with. So either one of these worth taking a look, and those are links here, so you can actually go and explore that on your own. The trusted the trusted applications. So those are apps, all right? They're like an application you would write, say, a binary that you would have running in Linux, or say an application running in Android. It uses the operating system APIs to actually talk to the operating system that is underneath and do whatever it is that it's trying to do. Obviously, it has to declare a channel that the driver on the other side is going to be able to use to talk to it. So effectively, the Linux driver is going to be able to say, I'm talking to, I don't know, some media DRM or a key management system on the other side, and these are the operations that I am trying to do. Interestingly, I actually found that it seems that some applications, some Android apps, can actually come with trusted apps. I haven't seen actual, code of that, but there seem to be hints as to effectively the trusted applications being dynamically loadable. This is where it gets a bit murky here, and there's not a lot of documentation, but it appears from stuff that I was looking at in terms of reading up on exploits and conversations about these things that this is something that can actually be done. Okay, so the channel, as I said, the trusted applications are going to give us a channel to the Linux side to talk to them. And so this is what's called, rich execution environment communication. So we're effectively trying to communicate back and forth between the Linux side and the trusted application. And there may be, say, a user space daemon to do that. It could be based on RAM. This is where it really is, kind of specific to the trusted execution environment that you are using. But you just need to know that effectively you've got some communication going back and forth in some sort of channel between those two sides, because otherwise it's completely useless. All right, secure storage. So this actually took me quite a bit of time to find out and figure out, because if you look at Google's Android documentation, they say that such and such has to be secured into hardware-backed storage or something of that kind. And then they kind of never tell you what that is. And after a while, I eventually found this thing called RPBM, so Replay Protected Memory Block. So apparently the eMMC chips, or say SD cards, have a special block in there that serves this RPBM. It contains effectively some authentication tokens that are burned from factory, and also they actually are going to match one-time programmable HUCs, hardware unique keys. So in other words, kind of like, to make a long story short, when you're programming a board at factory time, you're going to burn a key in the eMMC, burn a key in the SOC, and those two things are going to make sure that the communication between those two things is encrypted. or secured in some way, shape, or form. In fact, it kind of gets a bit fancy here because you see here trusted execution environment, rich execution environment, external storage. So effectively, if you have a trusted application that needs to talk to secure storage, it actually creates a packet that is sent off to the driver in the rich execution environment, and then that driver sends it off to the actual storage device, because effectively the eMMC is under Linux's control, so the trusted application can't write to the SD card. Linux can. So if you are Linux and you're sending a request to a trusted application and it needs to write to secure storage, effectively the map is I'm making a call from Android app into some Android subsystem that needs security. It turns around, makes a call into trusted execution environment, trusted application. The trusted application needs to read or write from storage. It sends a message back to Linux, rich execution environment, to have it write or read from the eMMC, and then kind of go back the other way around. It's kind of a bit involved, but that seems to be the path that is taken. And so the part of the replay protected part, the part that says replay protected, the idea here is if you grab one of those frames and you try to replay it, it won't work. Every frame that you send off to the RPBM part of the eMMC is effectively unique, and you can't reuse the same thing. So somebody listening in on the conversation can't actually repeat the conversation. Only a proper party on the SOC, namely a trusted application on the running on the trusted execution environment, is able to actually have a legitimate conversation with this stuff, right? And there's virtually no information about this out there except from some presentations that I found on the net from either ARM, like this was the best diagram I could ever I could find about that, and there I think there's a presentation or two from a Linaro Connect conference that you can find. All right. If you want to take a look at some Trusty TA applications, let me see if I can actually click on this link and go to it and show you a few things. So this is hosted on android.googlesource.com. All right, let's see if I can get to this new tab. Here we go. So AVB, all right, Android Verified Boot. Keymaster for effectively verifying passwords and pins and stuff, Keymaster for secure storage, and a few different applications here. So effectively a lot of the, and we'll see that later, a lot of the security related functionality in Android relies on those trusted applications. And those trusted applications are going to be implemented as trustee apps or whatever else to do the proper job. Okay, which gets me to, so since now we've covered the hardware, we've covered the TrustZone or trusted execution environment, which is very important for a lot of the operations that are done by Android. Let's take a look now at the high-level operating system, in this case, the Linux kernel. So Linux has a lot of security mechanisms built into it. Namely, for example, process isolation. Every process gets its own memory space. Discretionary access controls, these are the regular file system access controls. LSM hooks, the Linux security module hooks, which are used for SELinux and SEAndroid. The device mapper stuff, which can be used for full disk encryption, or is also used for the DMVerity for checking the integrity of the systems, the images that are written, and so on. A whole bunch of things here that Linux provides. And there's more. I'm just kind of mentioning the things that may be used in an Android context. Which then gets me to the full picture of the booting process. All right. So remember the earlier diagram was kind of like just this part here, and now we're actually looking at the full picture with everything that is getting booted. So we're adding a few things. We're adding AOSP. The Android open source project, which is Android sources available on android.googlesource.com. We're adding the Linux kernel and a whole bunch of images generated from that. All right, so let's start with the continuation here of the boot process. So I already showed you my SOC has these efuses which have the hash of some certificate chain. They make sure that the certificate chain that's being loaded and the secondary bootloader are properly signed, and the whole kind of stuff here gets me booted a little kernel and a trusted execution environment. And those two things might talk to each other to actually, as I said, provide the bootloader might actually tell the trusted execution environment, I'm going to load a properly verified image, or I'm not going to load a properly verified image, and then the TE will hold this for later use. Little kernel here, which is kind of like the first external bootloader being loaded, is then going to proceed to load and run the boot image. And in the case of Android, the boot image includes the Linux kernel, and it is generated by the AOSP. So let me kind of go back to this part of the diagram and explain to you what's going on. So the gray stuff is upstream open source projects, so be it the Linux kernel itself or just general open source projects. So the Linux kernel is taken by Google, and Google modifies it, adds it a few things for every new version of Android if they add some features. And so this is the, say, let's call this, kernel generic. And then effectively you've got kernel, MSM and whatever else, and the other kernels that are derived from that. So this kernel is then going to be taken by the SOC vendor, which is then going to customize it, put it in their SOC vendor AOSP. And speaking of the AOSP, so this is what's released by Google. These are the Android sources. And the Android sources themselves come from or contain a bunch of projects that are maintained open source independently of Google. So Google's going to take stuff from there as well. And then that's going to be taken by the SOC vendor, merging with the AOSP, gives us a AOSP that the OEM then uses to create a product. This is usually the crowd that I speak to, so the folks that are actually working on these OEM implementations. Aside from the conversation we have with SOC vendors, so a lot of the people that we work with are actually manufacturing Android devices. So the OEM is going to generate their own keys. Again, keep in mind that we've got all this keying system going on, so we're going to use images to sign keys to sign images, keys to sign APKs. And so the OEM build is going to generate us a boot image, and we also may have VB meta, so this is verified boot meta information. Either in the older versions of Android, the boot image will check that the incoming image, system image, is properly hashed, or in the case of VB meta, that is going to be done through the VB verified boot process. And effectively, it's going to check that the different images are properly signed. And there's a whole set of documentation about that. There's a lot of documentation from Google about the verified boot and all that kind of stuff. So at the boot's time, we're going to check that those images are properly booted, and then effectively let them boot later on. If they're not properly signed, effectively the boot process will fail. So as you can see, it's pretty complicated actually to get a secure system to boot. And even if you trust all this, just kind of highlight this here. So remember that open source projects are effectively community projects. There's people contributing code to those things. And so we are dependent on good faith at some point here from people making contributions. And it has been seen in the past, at least in the Linux kernel, people trying to submit patches that seemed legit, but were actually, some sort of backdoors that were being installed or pushed, and fortunately some of those have been identified, and this hasn't happened yet, as we know. But there are some attempts every so often at trying to get illegitimate code into open source projects. All right. So this is my verified boot process from and how Linux kind of comes into the picture of it. Effectively here, it's going to use the DMVerity stuff that I showed you, that I'm going to show you later on, to enforce the security of the system image and any other kind of image like that. Okay, full disk encryption. So if I'm using full disk encryption, which is kind of like the older way of doing things in Android, we're going to be using DMCrypt, which is part of the DMVerity, so the device mapper, not part of the device mapper Verity, part of device mapper functionality. So the device mapper functionality is a layer in the Linux kernel that allows us to insert a software abstraction between file system and hardware access. So in this case, DMCrypt is being used to ensure that the entirety of the disk is encrypted. And this is going to go under, say, ext4 and off to the block layer that's happening further down. Now, Full disk encryption is interesting. It makes sure that the entire volume is encrypted, but it has its drawbacks. Namely, if you're using full disk encryption, then the trouble that you're going to run into is the person using the device has to enter their credentials before the device can completely boot. And that's a bit problematic. So one of the things they introduced after full disk encryption is file-based encryption. And in this case, the way it works is you create an empty directory and you say, I'm going to secure this directory with these credentials, and you hand over the keys to the kernel for that, and then the kernel is going to be able to write the stuff to that directory and any of its subdirectories using those keys. And presumably those keys are being stashed away in a secure fashion using the harder back storage stuff that we discussed earlier. And what this does really in effect is it allows the Android device to boot straight into effectively the lock screen, and until the user has entered their credentials, then the data that belongs to them is off limits, all right? And it's not off limits just because the screen is locked, it's completely off limits because it's actually encrypted until the user enters their credentials, and then effectively the proper keys are retrieved from wherever they're stored, provided to the kernel, so the kernel can actually start accessing the information in that directory. And this is kind of like this is the presentation by my friend Gilad Ben Yosef called Protecting Your System from the Scum of the Universe. Have a look at that. Pretty interesting presentation. And he gives us a good view here of how file-based encryption works. Which gets me to SELinux and SEAndroid. So, okay, I had followed the SELinux and SEAndroid stuff, actually, so let's talk about SELinux for a second, put SEAndroid stuff on the side. So I've been following the SELinux stuff since the very beginning, when there were still discussions on the kernel mailing list about the Linux security module hooks and all that kind of stuff. And every time I tried to kind of approach SELinux and thereafter SEAndroid, I felt that I was hitting a brick wall. I tend to think that I'm fairly good at understanding stuff, and I try to as much as possible learn on my own. But this is one that had for years escaped my understanding. Every few years I would sit down and say, okay, now I'm going to understand SELinux, and I'd take a look at it, and it just never would happen, right? And actually, to eventually get myself to understand it, I had to go back and really read stuff that was written in the 1970s and 80s about some desire within effectively the defense community in the United States to get an operating system to be secure. And it's really just by reading up on this early stuff that I eventually understood, okay, this is why it works this way, and these are the things that make it work. But I mean, just reading the official SELinux documentation and SEAndroid documentation, at least for me, did not cut it, right? So there's only so much I can show you in this short presentation about SELinux and SEAndroid. In the other slide set, which I mentioned earlier about, that is the Android security internals class material, I've got about 125 slides just about this. So have fun, go look at that if you are interested into delving into this more deeply, all right? So let me just kind of give you a kind of what I was saying a moment ago. So kind of a rundown of my appreciation of the difficulty that SELinux and SEAndroid present. So there's a lot of stuff that is unreferenced and undocumented. So those early documents that I mentioned to you, that I found, that I read, were not necessarily directly linked from most of the SELinux and SEAndroid documentation that I could find. I had to go really back to some early literature and research papers that were published about SELinux and SEAndroid to actually start finding those early links and then walk back from those early links to the present time, all right? But the current documentation just talks to you about these concepts and from my perspective at least, asks you to just take them and run with them in good faith, and I can't. I mean, every time, for example, like every time you look at an SELinux policy, it's got these 4 fields, and I couldn't for the life of me understand what are those 4 fields and why are those 4 the ones we chose, not something else. So that's not something that you figure out just by looking at the current documentation. So yeah, quite a few concepts there, lumps together a lot of stuff. Yeah, so almost always invariably presented without reference to the early work that had been done in the 70s and 80s. I think that this is really kind of like one of the biggest critiques I think I can have with regards to the documentation of SELinux and SEAndroid. Okay, so right, yeah, different names for different stuff. Yeah, so this here. So the vast majority of the documentation about it assumes that you're just going to absorb like the semantics of it and not ask any questions. Again, this is one part that I couldn't do. Ted Cho, if you don't know Ted, I'm sure you're using his work anyway. Famous kernel developer, maintainer ext2, ext3, ext4, and so on. He tried SELinux, and his quote, I love it, is "Life is too short for SE to enable SELinux." And the deal is, when SELinux came out and was integrated into Linux kernel, I remember quite a few people that I knew were like, "Oh, cool, we've got a very secure operating system. Let me go ahead and enable this." And most people that tried it eventually said, "Okay, you know what? This is just too much trouble. I am not going to do that." And so most desktop systems don't necessarily kind of use the functionality. A lot of the server systems, enterprise and whatever government do use that stuff, but like if you're using Red Hat and things like that, Red Hat maintains rules for their own stuff to make them work, but most people don't. And so this is Linus's take. In 2009, I'll let you read that the second phrase of the second paragraph, kind of entertaining. So this is before they put Linus on a 7-second delay. So effectively, a lot of very talented people think this is complicated. All right. So if you've hit the wall trying to get fixing your SEAndroid rules to work on your device, don't despair. It's not because you're not smart. It's because it's really seriously complicated, and the documentation doesn't help you in any regard whatsoever. Okay. So generally speaking, what does SELinux and SEAndroid do? Effectively, it makes sure that unless you are specifically granted a right, then you get an access denied. It's a very simple rule. Unless you have a program that is configured to access file called foobar, then program will not be able to access file foobar, even if the discretionary access controls, in other words, the username and so the user ID and the file system permission of the file match. That won't really matter unless some SELinux rule says you can access the thing. You're going to get an EPERM. All right. There are different modes for SELinux, either permissive or enforcing or disabled. In the case of permissive, what will happen is if a rule is broken, or in other words, you try to access something you're not supposed to access, it's going to log an error, but it's going to still let you access the resource. If it is enforcing, then you're gonna get an EPERM. All right, go back to my EPERM. If it is disabled, then it's not either enforcing or permissive. It's just not working, and whatever it is that you had before, which is discretionary access controls, is what's going to actually work. Which gets me to the security contexts. So whenever you look at an SELinux rule, it's going to have this user::mode::type::MLS level. This is the thing that really completely confused me for years. Every time I looked at it, it's like, okay, why? Why are those 4 fields there? Why don't I have a 5th field? Why did I choose those 4? And the only way to make sense of that is to really go back into the history of all the trusted computing environments that the defense community wanted to put in place in the United States, that you actually start kind of cluing in as to, okay, this is what they're trying to do here. All right. If you don't do that, you're going to have to take this as an article of faith and go with it and say, okay, this is what we got. Right. All right. So the core policies, MLS. So multi-level security. So the idea, this is a diagram from Red Hat presentation. Effectively, multi-level security is one of the first attempts at creating secure systems, computing systems. And the idea here is, think of it in military terms, right? You have a senior staff that can read reports from a less senior staff, and less senior staff can write reports to senior people, but can't read the reports that are written by more senior people. That's really this multi-level security thing here, right? Think of, general versus, colonel versus, soldier, whatever else, and what they could do and could not do with regards to actual access to security. This is part of the security context that is used in SELinux and SEAndroid. SEAndroid doesn't use MLS. So this is here, I believe is always, it's always the same thing, so you can ignore that. Type enforcement is the key thing that is used in SEAndroid, all right? So out of the 4 fields that you got, that's the one that has the most use, all right? In fact, it's the only one that has any use. And this is why when you go in the actual rules under system, SELinux or SE policy, I can't remember what the specific path is, what you see is .te files because we're using type enforcement. And let me kind of try to describe it to you in a very, very simple way. So every object in a Linux system, everything that you've got, be it a process, be it a socket, be it a file, what have you, is part of a class, all right? So we're effectively going to typify the objects that we have. And for every class, we're going to say that it's got these different ways that it can be accessed. So a file can be opened, read, whatever. A process can use these calls and so on and so forth. And so what you're going to have to do is going to say, for an object of this class to access an object of that class, these are going to be the actual operations that will be allowed. And this is really what you're seeing here. So you've got an object, you've got a subject that is trying to access an object, and the object has a type, a class, and a set of operations. So what you can do is you can label the objects, and you're going to also label the subjects. And this is why this is the word type here being used in the 2 parts, because effectively you have a subject trying to access an object that you could use different names for them, but really they're just going to belong in a type. I'm going to say this subject is part of this type, and that object is belong to that type. And for these specific named types to interact, the rules will be the following. And so that's really what type enforcement is about. And all of the rules, as I said, in Android are based on this model right here. So if you actually want to understand type enforcement and go back to its original root, there is a paper which is referenced somewhere in my slides here or my other slide set about a 1985 article that specifically introduces type enforcement and explains how it's supposed to operate and so on and so forth. So this is really the essence, or like the reference document for me at least, for type enforcement. Role-based access control. So this is a different security model that was explained in a 1990-ish paper that you can also find in one of my references. And the idea here is you've got different users can have different roles, and then depending on the role that they have, they may or may not have access to certain capability or do a certain operation. In Android, that's not used. All right, it's effectively object R, I think. No, sorry, can't remember what it is in Android. What do we have in Android again? I'll have to look back at it. But effectively, all objects are object R. And in let me go check my tree here. Since let me actually go do this. So let me try to just change the colors here, so it might actually be able to. You guys might be able to see it better. For some reason, I've got a delay on my mouse. Sorry. All right, so let me go here to, and let me make this bigger. This. All right, so we are going to go under System, SE Policy. There we go. So this is the directory of the SE policies. If I go to private, I'm just going to drag one of these things down. So, yeah, okay. No, just clear. Less file contexts. Oops. Yeah, so. These are actual objects, and effectively, if I go up here, no, down, not up, object R. So most of this stuff is U object. So yeah, and the first field, so the MLS actually is S0, the user is U. We've always got these object R, and then effectively this is the type. So where it says MTP device and PMSG device, these are the types. So most of these rules say, in Android say U object R, S0 at the end, and effectively the type is what we've got as the third part. Let me see if I can show you something else here from the TE files that is representative. So we've got file context. Let's go check for service context or something like that. Service contexts. All right, so you see here, again, U object R, this is the type, account service, activity service, and then again, S0. So as I told you, effectively in Android, even though you've got the 4 fields that are present, we're mostly not using them. We're just using just the type enforcement. Okay, user-based access control is another set of IDs separate from the Unix IDs, and the idea is that they don't like the regular UID model because it often changes without, for example, as being a super user, and then effectively becomes detached from the actual objects. So the idea here is the user-based access controls enshrined in SELinux provide a more rigorous enforcement of the IDs that are chosen in this context. And again, mostly unused in the case of Android. So these are some quotes that I found in some of the older papers, and I really like them because they kind of present to the reader the real life kind of experience with working with the stuff. So it says here, from the small portion of the policy configuration, it is clear that the flexibility of the mandatory access control also yields a corresponding increase in the complexity of managing the security policy. All right, creating and maintaining configuration to meet a security is consistent with those requirements. In order for SELinux to be widely and used, a collection of base policy configurations must be developed to meet common set of security requirements to allow its use by end users with no security expertise. So in other words, they understood, all right, from the get-go that this is hard stuff, all right, and that users aren't supposed to be expected to understand this. That and in fact, if you look historically, it took years for these SELinux rules to be properly written down for common components in distributions such as whatever Apache and MySQL and what have you. The way SELinux works inside the Linux kernel is it relies on the LSM hooks, the Linux Security Module hooks. And this is a, like for example, taken from one of the early presentations about this in the early 2000s, a diagram that shows you how this works. So when you make an open system call, for example, looks up the inode, does some error checking, does discretionary access controls. Up to this point, this is regular Linux stuff. There's nothing that SELinux adds that is different. However, once the discretionary access controls have been made, there's an LSM hook that actually calls into the security engine and then says, do you want to allow this? Right? And assume here that we've got SELinux, and so SELinux would actually look up in the rules, see what the two types interacting are doing, and see if it has rules allowing this interaction. So for example, is type A allowed to talk to type B with this specific operation? And if so, it says, yeah, okay, go ahead. And then effectively the operation can go through. And obviously if there is no SELinux rule that says it is allowed, then as I said earlier, by default, you get an EPERM. You're denied. All right, this is a diagram that I got from this document called the SELinux Notebook. Pretty interesting, and effectively what you've got here is kind of like the complete map of, say, modern day SELinux. And as you can see, it's pretty involved. So the key thing for SELinux to operate, and so this one kind of took me a bit of time to wrap my head around, is you have to have a file system with tagged objects on it, effectively tagged files. So if you go on an Android device and you type ls-capital Z, you'll see that the files that are there actually have an SELinux type attached to them. So the file systems have to be labeled with the extended attributes. So the extended attributes is a functionality in the some Linux file systems that allows to add, say, out-of-band information about a file. So you can see the content of the file, you can see timestamps, users, and some extended attributes. And then extended attributes will have effectively the type that is associated to a binary. And you can have SELinux rules that say that when you're running a binary of this type, then you enter this domain, in other words, another type. And so then you can have rules that say this domain can access these different objects. And this is really how all of the SELinux and SEAndroid rule set works. So you start from a binary that's in a file system that has a specific tag, and you say when this binary runs, it goes into this domain, and then you say this domain can access these different files or types of files, and then you're going to also tag the files themselves, including the device entries under /dev and sysfs entries and so on. And so this is going to constrain what that domain can do, aka what the process on the disk can do. And the process on the disk started from a binary which is tagged effectively with these extended attributes. So we load rules into the SELinux module or kernel side of things, which uses the LSM hooks to actually check whether the access requested is permitted or not. And then in user space, you've of course got a whole bunch of stuff in here, including you could have SELinux aware applications. Effectively, this could have a bunch of daemons that know about SELinux, and effectively that's the same thing that SEAndroid does. So SEAndroid has some user space components that know about the SELinux rules and will use that to actually allow you or not allow you to do things. So for example, the properties, when you do get prop and whatever else, they have associated SELinux policies. The properties are managed by the init process. And so that's going to use the associated rules for changing and accessing those, just changing those properties to allow or disallow the change of a property. So this is a case where you have a user space component that also speaks SELinux. And then you can have, this is effectively kind of like just the generation of the SELinux policies. This, in the case of Android, is done at build time. So when you build Android, this system SE policy stuff is being used, in addition to what specific rules you may have under device. So if you're going to device, manufacturer, product name, and you have some SELinux policies in there, they could also contribute to this generation of SELinux policies. And if you've packaged a device before, you might have encountered cases when you build the system and effectively you hit a do not allow rule or never allow rule, sorry. If you get a never allow rule, that's because somebody within the Android team effectively said, okay, we never want a vendor to actually give these permissions. And so when you build your AOSP, the build system will say, sorry, you're not allowed to do that. You have to understand that the never allow rules are actually done or taken care of only at build time. So effectively, there's nothing in the engine down here that actually is going to say, oh, well, there's a never allow rule, so we can't actually allow that. It's just at build time. You will get the error that says never allow such and such, and then you are trying to give this access, and then the build system will say, no, you can't do that. Of course, you can try to remove the never allow rule by hand if you want to, but then you are not going to pass the certification process that Google is going to want to do if you are trying to get certification from them. And generally speaking, it's not good policy. I mean, if they put that in there, there's a good reason for them to do that. So even if you're doing an embedded device where you don't care about certification, you may want to tread carefully there about removing never allow rules. Okay, which gets me into user space. As I said, there's a whole bunch of stuff that I could say about SELinux here that I just don't have the bandwidth to cover. So you go to stuff like ADB. So okay, ADB, again, this is a diagram you might have seen in my previous presentations. We've got the host with the ADB server talking to an ADB-D daemon on the other side over USB or TCP/IP. Now there is some crypto stuff involved in ADB. And you can check out the sources of ADB. I think I have the reference in my other slide set. And if you wanted to kind of like lock the device down to a specific key, I think you need to change one liner somewhere in the sources to do that. Okay, app signing. So, along with all the rest of the secure booting stuff, you have to get into a state where, some applications may have some privileges that others do not. So in the case of Android, all certificates are self-signed. In other words, Google does not check that you've got a certificate from a certificate authority or any of that kind of stuff. you self-certify that you're Mickey Mouse. There's no way for Google to actually check that, except when Disney complains, they'll remove your app from the store, that kind of stuff, right? There are some signatures that if you actually use them, you're going to get some privileges that you are not going to usually get. That is the case, for example, for the platform key and some other keys which are built into the AOSP. Obviously, you can extend the permission model if you want. You can check whether the app calling you has certain signed with some certain keys and so on and so forth. All right. The component that manages permissions in Android is called the package manager. It is the authority about the signature of all apps. And effectively, there is a bunch of code inside the framework that is going to check the signature of the caller, right? So check calling permission, check enforce calling permission. So when a system service gets a call, it can check whether the remote app has permissions to actually check, to actually do what operations are going to be doing. So effectively here, the package manager is the main component that allows us to do permission checking, and some of this permission checking is based on the signatures which I mentioned just previously. Okay, OTA. So there's two main paths for over-the-air upgrades. There's the recovery mode, and in the case of the recovery mode, what happens there is you reboot into recovery, you burn the update, and then you reboot into the update. And then you've got effectively also AB updates, and the idea behind AB updates is while you're running, say, A, you update B, and then you reboot into B, and then if you check that the B has properly booted, you say, okay, B is now the new proper thing, and then we're not going to reboot back into A, but if B fails, then you reboot and you go back to A. The idea with this is we don't want the user to actually see that there's an OTA happening or never understand that the system is going in a special mode of operation here where they're not seeing Android. So that's the job of the AB updates. There is a mode, or some devices might have streaming support for AB updates. In that case, what happens is, as this stuff is being downloaded, it goes straight into the actual B partition if I'm in A, and then once it's completely downloaded, then we check the signature of what was just burned, and if it's good, then we can actually go ahead and boot it. Otherwise, we just download the whole thing, we write it to B, and then we proceed from there. So this is the streaming support. Is actually a SOC vendor. This it's not the AB support, but really the streaming support that is hardware dependent. Okay, Google's on-device security mechanisms. So when you buy an Android device that is properly certified, you can have this thing called Safety Net, which talks to the backend, and that continuously does a whole bunch of things like verifying applications, providing attestation, and so on and so forth. So this is provided by Google. I don't believe this is open source, but there's information about it on the net if you want to go check this out. Which gets me to link back to the hardware discussion that we were having earlier. Key store and key master. If you are securely storing keys in Android, you're talking to the key store. The key store system service or component or daemon is going to use the keymaster HAL to talk to a keymaster application running on the trusted operating system in secure mode. All right. So effectively, this ties in and all the TrustZone stuff that we were talking about earlier, and ensures that the keys that you're storing are going to be properly secured onto whatever hardware-backed storage or RPMB in the case of eMMC. Where it's going to be safely stored away from prying eyes and whatever else. So in other words, if you were to shut this device down, take the eMMC off and put it in somewhere else, there's no way for actually anybody to retrieve the keys that you wrote from your application. All right, the eMMC will only function with the specific SOC that has been tied to. Logging in, same kind of concept. When you put a pattern in or fingerprint or whatever else, it's also going to go over a trusted execution environment into either the fingerprint trusted application or the gatekeeper trusted application, and then allow you to then access keys associated with this identifier that you've properly identified for. Okay. Again, we're using TrustZone here to ensure that the checks that are being done are done in a secure fashion. All right. DRM. So this is a diagram that I got from a presentation by Inforce, and I'm not going to walk you through the entire thing, but you can, if you just look at it really quickly, you'll see that again we are relying on the trusted execution environment here to enable the hardware to do something that would otherwise not be allowed to do. All right. In this case, we're going to provide the DRM agent in the TrustZone side is going to allow or not the playback of the DRM content. So this is how, say, again, trusted execution allows us to do stuff that we wouldn't be able to do just with plain Linux. Okay, Android framework for work. This is fairly high level, but effectively there is a way for enterprise users to control what happens on the devices, and there's a fair amount of information about that on Google's website, so I'm just kind of like leaving those slides here as reference more than anything else. So you can have effectively the default Android app, I believe, which one is that? You can have the default Android device policy manager on the device. Or you can create your own specific thing, and then you have to use their own their APIs and so on and so forth. All right. Okay. What does Google have in its infrastructure? So up to now, we effectively covered what happens on the device, from the hardware all the way into the applications. Now we're off to the cloud itself. So in other words, there are apps which are stored by Google, which are delivered to devices. And the question is, what is Google doing to make sure that those applications are okay? So it does actually have a scanner that goes around and checks applications, and then either notifies the app developer that there's some issue with them, suspends the application, and if it's really offending, and do whatever else is required. And I can tell you this works for real, because we had an application that we had put there, which had an outdated SSL library, and we had an email from them coming in saying, okay, your application here is using an outdated SSL library. You have X amount of time to remedy this. Otherwise, we're going to effectively just delist your application. And so it might be frustrating a bit for a developer, but it makes sense from a user's perspective. You don't want to have, a problematic application sitting there that could be exploited, or could effectively cause any issues along the way. All right. So that's a pretty quick rundown here of Android's security mechanism from the ground up. And I'm going to stick around here for a few more minutes, see if there are any questions that either come from chat or over the real-time link that I've got with some of the audience. And otherwise, if you are going to sign off, then thank you for attending. Or if you're watching this afterwards and you find any sort of kinks or issues that in what I've explained, please let me know. I'm happy to add corrections after the fact. So there's a bit of a delay here between my speaking and people typing, so I might not have finished speaking for people to start actually typing questions yet. So I'll wait a bit more. So those of you watching the video later on might find that I'm just sitting here and doing nothing, but really it's just because I know there's about a minute delay between the my initial broadcast and people watching the video on their side. What about protection in Play Store? Protected by. Okay, so I have to admit that I'm not familiar with this. If it's something that's fairly new here, so I'll have to defer back on that. I'll check it out and possibly post a follow-up to that on the chat or the discussion on the video later on. Okay, seems to be that they're doing an additional check on uploaded apps besides the initial check. I'll definitely check it out. I'm sorry, I'd rather not, talk about something that I'm not directly familiar with, but I'll certainly check it out. It seems interesting. Okay, well, thank you folks for attending. I will be signing off, and if there are any more questions that come over chat, then I will try to pick them up as they come in due time. All right, thank you again, and hope to join you again for another live stream at some point soon in the future.